Hey, all right. I'm going to try a video solution here. And I got a question on 24, but 24 and 25 are both triangles, and they're kind of hard ones. So I thought I would kind of tie this together here. They're kind of a one and the same. And they really begin with trying to understand, what a standing wave pattern is. Let me draw the easiest one. Let's say I had some kind of wall, and hopefully you saw this in the video solution, where if I tie some kind of string and then shake it, this wave pattern will form. And the wave pattern won't look like it's traveling, it'll just kind of look like it's breathing. And that's why we call it a standing wave. But if both ends are tied, then they can't move. Now, the rest of it is free to move, but there are some interesting and magical points. And so I'll draw the wave at this point, but you almost need to see this on the lecture videos to realize that the crests don't move along like I'll call it a normal wave, a traveling wave. They more breathe. So this crest up here, a moment later, moves downward, and these troughs move upward, and the wave sort of looks like this a moment later. Now, a moment later after that, it moves even further down, and it looks kind of like a straight line. All the crests come down, and all the troughs come up. Then a moment after that, it continues to go up for the troughs and continues to go down for the crests. And I'm not even sure we should call them crests anymore now that they're down. And then eventually, what was up here as a crest is now down here as a full trough. And what was down here, well, I guess I went a little far. But what was here as a full trough is now a crest. And we've kind of reversed roles. Everything that was a crest is now a trough, and everything's a trough that's now a crest. Now, I hope my picture doesn't look too busy, but this is not the wave at one moment in time. This is a picture of the wave at multiple moments in time, and it's trying to give you the best I can with a drawing of what the wave pattern would look like. And the thing to remember then is there are these points that, even though they're not clamped down like the endpoints here, they don't move also. And those points are referred to as the nodes. And these points that go from crest to trough, back to crest to trough, these points, because they move the most, are called antinodes. And so we're going to focus on that. So antinodes I'll label with an AN and node with an N. All right, so the way to understand both of these problems, 25 and 24, and starting with number 25, let's read it here. It says, what is the fundamental frequency of a rope that is 4 meters long that is tied at both ends? Now, what I like to do is just in my mind draw kind of a standing wave pattern without worrying about where the ends are right now. And then read carefully here on what it's presented, because it says here the rope is 4 meters long. Okay, that's good to know. And then it's tied at both ends. So tied at both ends means one end, both ends actually, are nodes. And so it looks very much like the pattern I've drawn up here. This is the easiest one. That's why I drew it first. All right. And so maybe I'll just, and it doesn't matter which one I pick, because if you imagine this thing kind of breathing, this would be a node, 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 this would be a node. Okay? And so it could be in this kind of pattern. It could be in a pattern where you have a node here and a node here, and it looks like then we got 1, 2, 3, 4 freely standing nodes. Okay? Or the one I drew up here, 1, 2, 3, well, that's the same thing, 4 nodes there. But it could be something like this. It could be where this is a node and this is a node, and you got one freely standing node. But for this problem, it says, what is the fundamental? And that gives it away. The fundamental would be the lowest frequency or longest wavelength. And we know that it is 4 meters from node to node. So the one that would make the longest wavelength is where this was the 4 meters. Well, you could picture it here if you would rather. It doesn't really matter. I just drew one so I can kind of forget about the rest. So forgetting about the rest, they're saying that I have a pattern that looks something like this. It's 4 meters long, and it represents just one hump, node to node, which hopefully in the bigger picture you can see that that one hump is really a half a wavelength. So the way to answer these problems is you got to visualize this picture. That's why I'm spending so much on this picture. There's not really a formula, although we can derive a formula from them, and I do in the video lectures. But I could just see, okay, that, you know, if I'm looking at the whole thing, node to node is a half wavelength. So I'll put 1/2 a wavelength is 4 meters, which means the wavelength is 8 meters. Okay, so there's the wavelength. That's how you get the wavelength. And that's the hard part of these problems. Now, the rest of it's pretty easy because it says, what is the fundamental frequency? And they do give you the speed, and we know velocity is wavelength times the frequency. So the problem goes on to say that the speed is 20 meters per second, and we just did the wavelength of 8 meters. So we can then move the 8 over to here. That would go into 2.5 times, and we would have per second. And so we would have a frequency of 2.5 hertz. And that's the longest wavelength / lowest frequency. That is the fundamental one. Now, there's other patterns that could be there, but I'll leave that alone for now. That's not part of this problem. So I'll just say, okay, we're done with 2025. Now, keep that same idea in mind for number 24. Because 24 says you have a 2 meter long rope that is tied to a very thin string so that the end is essentially free to move. What are the possible wavelengths, or what possible wavelengths will produce standing wave patterns? So why don't I just draw, so I can kind of have it in my mind, a standing wave pattern. And somewhere the rope transitions from, they don't say big and heavy, but I'm going to call it big and heavy because then they go to thin and light. Okay, so the first part of it tells me the rope is 2 meters long. Okay, so from whatever to whatever, in this case, back on 25, it was node to node. I know it's 4 meters. I know that from point 1 to point 2, whatever this is, the rope is 2 meters long. And it says it's very thin, so it's essentially free to move. So I think what they're implying is one end is tied, so one end of this big, thick rope is a node. All right, so looking across this, and I'll just say this is the end that's tied right there. That'll be the node. Okay, and then I can forget about the rest. Okay, and then the pattern would look something like this. But unlike 25, where the other end was tied and had to be a node, they're trying to say in this that the other end is free to move, and that would make it an antinode. So this crest, which again, maybe I should draw at least one other moment in time, would later on become a trough, and this trough later on would become a crest. And again, I hope my drawing isn't too busy. I'll only draw 2 moments in time so it doesn't look too complicated. But when I do that, I might have lost track. Maybe I should have done that in a different color. But this would have been a crest. This would be a trough. Let's make it a little darker. This would be a crest. This would be a trough at a given moment in time. This would be a crest. This would be a trough, crest, and a trough. And so I have antinode here, and this would be an antinode because it would go up later on. This would be an antinode. So all these peaks would represent antinodes. All these places down here that cross would represent a node. And they're saying here that it is free to move, but they don't say much more than that. So they are trying to really say this end would be an antinode. So it could be like, say, right here. I'll just draw and forget about the rest. But it doesn't have to be. It could be here and forget about the rest. So now you can see why there's different combinations, because we know from the first tied point to the end of the thick string where the thin one begins, this is 2 meters. So we know 2 meters could be what? Now, if you look at what I'm drawing right here, and so you're at an antinode, you would go 1 wavelength and a quarter. So that would be 1 1/4 wavelengths, which maybe I will write as 5/4. And now the reason why is, watch. What if I did the first one back here? It would be 1 wavelength, then another 1/2 wavelength, then another 1/4 wavelength. So that would be 1 3/4 or 5/4. Or what if I did one a little tighter in? Now, can you see every time I get a little tighter or a little bigger, I'm going from an antinode to an antinode. So that's a 1/2 wavelength. Because remember, this antinode at this moment would be a crest, and at this moment would be a trough. And so as I switch where the other point may be, this would change by a 1/2. So that means if I moved in, if I took a 1/2 away, I would be at 3/4. And again, maybe you can see it here. If I draw it, there's a 1/2 wavelength and there's a 1/4. And if I come in a little tighter, the tightest I can get, this is the first antinode that's the closest to that node, that's a 1/4 wavelength. And if I started to go bigger, so back here, 1 3/4, and if I increase it by a 1/2 wavelength, that makes what? 2 1/4. And the next one, if I increase by a 1/2 wavelength, would be 2 3/4. And this I can write as 9/4, and this I can write as 11/4. Now, I didn't put them in order, but if you go to order of the smallest right here to the biggest right here, you'll see a pattern mathematically. You'll see 1/4, then you'll see 3/4, then you'll see 5/4, then you'll see 7/4, then you'll see 9/4, then you'll see 11/4. And so what you have is an odd integer over 4. So this 2 meter must equal an odd integer over 4. I'll write it this way, where m can be 1, 3, 5, 7, ... Oh, and wavelengths. I just counted the numbers, but this is how many wavelengths they are. So if we set m equal to 1, we'd be looking at from here to here, and we would say the 2 meters is a 1/4 wavelength. Okay. Now this m can look confusing. This m is a meter. Maybe I'll just cross it out so I don't confuse you. But this m is an integer. So if I move the 4 over here, we get 8 m lambdas. And then if I move the integer m underneath, I get that. Okay. So this is what this problem is saying, that my possible wavelengths are 8 and over 1 would work, 8 over 3 would work, 8 over 5 would work, 8 over 7 would work, ... So all 8 divided by any of the odd integers would be the possible wavelengths. So that's the harder one to visualize. And so I can see why you guys are asking about this one, number 24. It's a tough one, but really wanted to do 25 together with that because that leads into it. So 25 is a little easier. 24 is the hard one. All right, hope that helped.